Hello programmers. Welcome back. Today we're going to talk about a problem on permutations. The question or the problem statement is pretty simple. It says given an array nums of distinct integers, written all the possible permutations. So in order to provide the solution of it, we should understand a few things. In programming, when given with a problem statement, the initial input of n size at every step of the way, either be it iteration or recursion, your problem statement should get reduced little by little, right? So you're breaking the enormous problem into smaller chunks, or gradually on each iteration or recursion it should get smaller till you reach a base condition where your size is 0 or 1 or 2, whatever. If we do the same approach when we used to do Fibonacci series, or when we used to determine the factorial of a given number, this is no different. Although the logic is different, but the mindset is same. The problem statement should get reduced, right? But now let's look at what should be the logical mindset behind this particular problem to find the permutations of a number. I would say that if you think about a number, if you think about a number such as 1 comma 2, you know, it has one arrangement which is 1 comma 2 itself. This is arrangement 1. The second arrangement should be, or can be, obviously 2 comma 1, right? So what happened? 1 comma 2 in itself, this is my input, right? This is my input. Do understand? And what is my output? Different arrangements. One arrangement is 1 comma 2 itself. The input is the output. Why? Because I said, hey, there are two seats, okay, and there are two people. I said, hey, one would sit here and two would sit here. And on the second occasion I said, hey, one would sit here and two would sit here. So hence you got two arrangements, 1 2 and 2 1. Yes. If I take a bigger problem, 1 2 3 and 4, and if I try to think about a recursive approach, obviously, why did I say it is obvious? Because recursion is the natural choice when it comes to these type of problems of breaking a larger chunk to a smaller chunk, you know. So on recursion 1, let's say I decide, hey, 1, you fix yourself on 0th index, first index, second index, third index. These are indexes. Yes, index. I say that you fix yourself on index 0, you don't move. This is my rule on recursion level 1, and I say excuse me, 2 3 and 4 is subject to different arrangements. 2 can sit on index 1, or 2 can sit on index 2, or 2 can sit on index 3. I don't mind. But on recursion 1, my strict rule is the element 1 should be at seed 0. On recursion 2, element 1 is still fixed on seed 0 because that was the rule dictated from recursion 1. But recursion 2 now newly dictates, say 2 will stay here. This is my new rule. They shouldn't move. So only the elements 3 and 4 are subject to permutation. So you see the problem statement got reduced. Initially the problem statement was 4 elements, 1 2 3 4, different arrangements of 1 2 3 4. Yes, 4 elements. On recursion 1, at the end of recursion 1, when I was about to call recursion 2, I said, hey, now I just need to find out the different arrangements of 2 3 and 4, provided the element 1 is hard coded or is seated at element 0. At the end of recursion 2, I said, provided 1 is here and 2 is here, my problem statement is now different arrangements of only two elements, 3 and 4. And that's my input to recursion 3. At the end of recursion 3, when I'm about to call recursion 4 from recursion 3, I only have to find the different arrangements for only the element 4. And at recursion 4, I said that 1 will sit here, 2 will sit here, 3 will sit here. Means 1 will sit at index 0, 2 would be at index 1, 3 would be at index 2, and 4 would be at index 3. So you have prepared a complete arrangement. There's nothing else to play around with. All the elements are, you know, ordered to sit in these positions. So this is one arrangement. Can I create any other arrangement? You know, recursion is about going down then coming back up. So in a sense, you called R2 from R1, R3 from R2, R4 from R3, and now you would go back up. When you went back from R4 to R3, so at R3, these three were instructed to stay in these three positions, and R4, I mean, sorry, not R4, the element 4 was given the relaxation to sit in different seats, but there were only one seat left. Seat means index 3, because all the other seats were taken up by the element 1, 2 and 3. So you can't do much other than creating the pattern 1, 2, 3 and 4, because there's only one seat left. So from R3 you go back to R2, but from R2 now you can create a different path. R2, you instructed in recursion to 1 and 2 to be placed in these two seats, right? So 1 and 2 are still placed on seat number 0 and seat number 1. You can't do anything over here. That was the rule of R2. But instead of placing 3 in seat index 2, see, element 3 was placed at seat index 2, you don't do it. You swap. In a sense, you move element 4 to seat number 2, and you put this over here. So now at the end of R2, when you're about to call the new recursion 3, let's call it recursion 3 slash, you would say, hey, I have instructed 1, 2 and 4 to sit in their seats, and 3 is subject to arrangements. And from here, when you will move to the new recursion R4, you will say, hey, 1, 2, 4 and 3 are now instructed to sit in these positions or to place themselves in these indexes. So you get a new arrangement 1, 2, 4, 3, right? So two things I want to emphasize over here. As you could see that after every recursion, your problem statement, meaning the number of elements you're going to arrange, reduces by 1. Initially it was n or 4 elements, 1, 2, 3 and 4. After the end of first recursion, there were 3 elements to arrange. At the end of second recursion, there were 2 elements to arrange. At the end of third recursion, there was only 1 element to arrange. When you reached R4, you know, you saw that all the elements are now arranged in their positions, and we got one arrangement, and we stored that in my final output, or final collection. And that's how we produce recursively different arrangements. That's point number 1 to emphasize. Point number 2 is, in every recursion you make a choice and you say that, hey, this element is fixed over here. All the remaining elements, 1 minus this element, is now subject to um, arrangement, subject to permutation. So you are fixing an element. Obviously, you have to make that decision, right? Or else you can't get into finding different arrangement. You have to make a decision. My decision was to fix one at element 0, and all the other ones are subject to arrangements. Now to write this concept out in a in program, let's see what we can do. Since we want an output of list of integers, we would like to have it like this: list of integers. In the sense, we'll have output, yes, and we'll have it as an array list. I would also go as far as to write a swap function, because we would do swap, right? And then the two indexes. Let's say if the two indexes are the same, so you're swapping the same element, right? Which makes absolutely no sense. So I'll return. But if that's not the case, then obviously I can do a swap. No problem over here. Yes. And I hope this swapping function doesn't have any problem. Now on to the main logic. I'll say perm, right? I'll say this, and I'll have a variable called cpos. This is a new entry. What does this variable do? The purpose of cpos is to say from which index till which index I would like permutation to happen, right? But you would say cpos is only one variable. Yes, cpos tells you that from the left, from which index till the end of the array I would like permutations to happen, right? So if I call this from this function, the initial function, yes, I would say this, hey, this is nums and this is 0. That basically this 0 means from the zeroth element, zeroth zeroth element till the last element. find permutation, right? Now, if cpos is equal to nums dot length minus 1 means it has reached the last element, so there's nothing to arrange, right? I'll just store the final arrangement, whatever is in the nums array, into your final output list. How would I do that? Well, I will do an int stream of, and I will do a nums. Probably think box would be used because nums is a primitive and the outputs a list of integer wrapper class. um, Collect collectors. I think that would be it, and then I can do a return from here if I don't want to proceed any further. Now I'll have a variable I, which would be cpos, and then I would be nums.length because I want to iterate this from cpos to the length to the end of the array. And here's the thing, I'll swap. And if you don't understand why am I doing this, I'll give you an example and try to explain. Let's see. I believe this should work. Obviously, I should return the output. Sorry, the things are not formatted very well. Swap. I think I made a mistake. Basically, a typo. I think so. Okay, this should work. This should work. I think. Aha. This is a mistake. Suppose plus minus 1. Okay. Submit. Okay. There's room for optimization, but let me tell you the concept right now. So when I pass nums, which is my input array, and 0 means from the 0th element, this 0th element is basically cpos. Cpos in a sense current position. That's 0th element till the last element. Find permutation, right? Okay. Initially, cpos is 0. So this doesn't match. This is the base condition. It would match at the very end, not right now. I is equal to cpos. This basically means I is equal to 0 since cpos is equal to 0, right? What does this mean? This swaps the array. Let's say your initial array is 1, 2, 3, 4, and I and cpos both are 0. So basically you are doing a useless swap. You're repositioning the element 1, which is at the 0th position, in the same position. So 1 again sits in the 0th position. So 1, 2, 3, 4 becomes 1, 2, 3, 4. You might find this stupid, but it's really not. What does this tell me? That, hey, now this basically means at recursion 1, I have fixed 1 in this position, and all the remaining elements 2, 3, and 4 is subject to arrangement. So you see, at the start, when nums and at this particular stage, you had the entire array 1, 2, 3, come on, 2, 3, 4. This entire array to arrange. Yes, because your cpos was 0. That means you start from index 0 to till the end of the array and you find arrangements. When you did swap, 1, 2, 3, 4 became 1, 2, 3, 4. But this basically, what I want to emphasize is, after doing swap, what I want is, I say that, hey, 1 is now positioned strictly on 0th index. All the remaining elements, that's 2, 3, and 4, are subject to arrangement. How do I say that? I say that in the next line. I say that by passing CPOS plus 1. CPOS plus 1 means right now CPOS is 0. So the second, so this becomes 1, right? That basically means you start from first index till the end of the array. First index is 2. End of the array means 2, 3 and 4. So this part is now subject to permutation. 1 is fixed. Gradually, if you move on and look at further recursions, you would see I would fix 1 comma 2 and I would say, hey, 3 and 4 is now subject to permutation, and then 1 2 3 is fixed and 4 is only subject to permutation, and finally you will get 1 2 3 and 4, right? That is the way you're reducing the problem statement, the input size. You're fixing certain element and you're recursing over it to get your final set of, all the permutations possible. Yeah, I hope this problem makes sense. If you have any questions, do let me know. Thank you.